Okay, everybody, hello for the final time this term. Am I coming in loud and clear? Everybody, good morning, Steve. Hello. Obviously, it's a very sad lesson today because it's the final time that I'll be with you for the lectures. Anyway, I do have two tutorials later today. So look, let's just make the best of it and enjoy it. Um, my little friend Quokka, he's celebrating because, no more lectures. Anyway, yeah, yeah. Can you see the puppy? Where's the puppy? Up the back, yeah. See if we can do puppy cam. Let's see. Where's the pup? Let me see. Let me see. Yeah, you can see the pup right there. Hello. They've given up as well. Anyway, I hope you're well. And in today's lecture, we're going to finish the course, the calculus part of the course anyway. There will be, I think Captain Bill Ellis is going to do a revision lecture after this one. And then on Monday, I think there will be another calculus revision lecture. So there'll be lots of revision. Yeah, Steve, she made it to the bed. She just jumped up there one day. So obviously a sad time, but let's enjoy it. And the last thing we're going to talk about is inverse hyperbolic functions, right? So last time we introduced hyperbolic functions. Now, what about their inverses? So it's the very last lecture. Okay. So let me share my document camera. Oops. And yeah, inverse hyperbolic trig functions. Last time we talked about, hyperbolic sine, hyperbolic cos, hyperbolic tan. Now, what about their inverses? So that's what we're going to talk about, and we're going to look at the calculus associated with them, right? So in the previous lesson, we looked at things like, cosh x, sine x, and than x. So what about these functions? Do they have inverses? Can we differentiate? Can we integrate? And what are some interesting properties of the inverse of these functions? Okay, so that's the idea today. So before we do that, let me go to GeoGebra and we can have a look at what we're going to see today. Okay, so let me just share my GeoGebra window. Okay, so just to refresh everybody's memory, this was cosh, this was sine, and this was than, right? And they're all defined in terms of exponential functions. Okay, so if I have, say, the sine function, and I put in the line y equals x, inverse hyperbolic sine will just be reflected in that line y equals x, right? And it's the same for hyperbolic cosine. Although we have to be careful here because the graph is not a one-to-one graph. So all we do is restrict it to the positive x values, right? So you're just reflecting that half in the line y equals x, okay? And then what about the hyperbolic tan and the inverse of that? Well, again, you're just reflecting it. Okay, so they're a really basic way of understanding what the inverses look like based on the graph of the original function. And if you really want to break it down, you can break it down in terms of exponential functions for the hyperbolic cos and hyperbolic sine and hyperbolic tan. Okay, so let's get into some of our notes. And These are explicit representations for hyperbolic cosine or inverse hyperbolic cos, inverse hyperbolic sine, and inverse hyperbolic tan. Now, just a couple of things here. In these definitions, of course, in this one, we're assuming x is greater than or equal to 0. In this one, we're assuming x is between -1 and 1, right? Okay. Now, you don't need to remember these because remember, the final exam is an open book exam. So you're welcome to look at your notes and things like this. Okay. Because, I mean, these are not easy to remember anyway. But I thought what we could do is just derive some of these relationships, right? So from the graph that we saw before, hyperbolic sine is an increasing function. It must have an inverse. Let us derive the form of this inverse function. Well, here it is right here. So where does this come from? Let me go over here and I'll actually derive it. Okay. Now you might be asked to derive this in the exam. Who knows? But let's start. Where does this actually come from? Okay. So as a basic derivation, let's start with hyperbolic sine or shine. And we're going to write this in terms of exponentials. And remember, when we try to find inverse functions, we want to rearrange the variables. So we want to make x equal a function of y. Okay, so let's try that. So let's move the 2 up there. And I'm going to change the exponent on this one so it looks like this. Okay. Now, it's going to be quite hard to solve for x. So what we're going to do is solve this equation for e to the x. Okay. So if I cross multiply here, I can get this. Okay. So I'm not trying to solve for x here. I'm going to solve for e to the x. So let's move that over there. All right. So now this is an equation that we can do something with, believe it or not. Okay, so let's rearrange and I'll show you what's going on. So let's bring that to the other side. Okay. Now this looks like a strange equation, but I can actually write it like this. So it's a quadratic equation for e to the x. Okay, so that's a quadratic equation for e to the x that we can solve. Okay, a is 1, b will be -2y, and c will be -1. Okay, so if we solve it, we'll get e to the x equals y. So you're just using the quadratic formula now. Okay. Okay, so we only need the positive square root because e to the x is always positive. So you don't need to do plus or minus here. Okay. All right, so we're almost finished now. If that is that, let's rearrange. And so finally, we've got x as a function of y. So let's switch the variables, and we get this. Okay, so instead of log of that, you have log of that. Okay. So that's quite a long derivation, but that's really some justification on where this comes from. Okay, if you want the really simple idea, draw a graph. If you want the algebraic derivation, you can do something like this. Okay, but this is like, it's quite difficult because a lot of students don't know that, oh, we solve for e to the x first and then we get x. Okay. All right, so we're pretty happy about that. Woohoo. All right. So let's make that star. Go back here. So C star. Now, so that's shine inverse, or inverse shine. Our cosh function was not one-to-one. So let's just restrict it to, you know, the right-hand arc, and then using similar arguments to what we did up here, we can get this for cosh, the inverse of cosh, right? Now, hyperbolic tan is an increasing function, and again, you can come up with this, but I'm not going to do all the details here, right? So I think this is one of your tutorial questions, but all you have to do is basically follow this and change this minus to a plus, and it will just, you know, go through, do the quadratic formula. Okay. All right. So that's where it comes from. What about using these inverse functions in calculations? Okay. So let's have a look, and we can see some simple examples, and then we'll work up to some more challenging situations. All right, so this is a classic sort of entry-level example now. Determine the hyperbolic cos of inverse hyperbolic sine of 1/2. Okay, and so they might remind you of when you did, you know, cosine of sine inverse of something, right? So no hyperbolic stuff. All right, so we can do similar strategies with this one. And one strategy is to use the following identity. Okay, so let's compute cosh squared, and then we can take the square root of that, and we know the square root's positive because cosh cannot be negative, right? It's greater than or equal to 1. If I sort of go back to my graph up here, let me just switch over to GeoGebra, right? This is my cosh curve. Okay, so you see that cosh curve is positive, right? It's greater than or equal to 1. So whenever you take the hyperbolic cos of something, you can't get a negative value, right? So that's a pretty important thing when you're taking square roots, as we will for this one. Okay, so I'm going to let the t be this thing in here. So let's make some notes. So cosh squared of all this, that's what we'll work out first, and then we'll take the square root to find the original answer. Okay, so that by this equals 1 plus sine squared of this mess. Okay, and so what I would like to do there is say, well, that's just the square of this and get the inverses together. So this is 1 plus this. Okay, so I've just moved the squared out there just to make it a bit clearer. So this and this will cancel. So it'll be 1/2 squared. So this will be 1/4. So 1 plus 1/4, 5/4. So we've got the cosh squared of this, the square of this. So we don't want that. We want okay, we can take the positive square root because we don't care whether well, this can't be negative, right? You can't take the cosh of something and get a negative number. So it has to be the positive one. All right. So that's a sort of an entry level one, but this is a good starting point, right? This is a very good starting point. Steve, what do you mean? What do you maybe 1 plus sine squared needs to have breaks? What do you mean? Let me know. Okay, so that's just an entry level one. Nothing too serious there. So what about calculus? Okay, well, here are some derivatives: inverse hyperbolic sine, inverse hyperbolic cosine, and inverse hyperbolic tan. Okay, and again, remember, you don't need to memorize these or anything because you will have them in your exam, right? But where do these come from? Before we get to that, if this is true, then if you integrate something like this, you're going to get these ones on the left. Okay, so if you know this is true, then you integrate this to get this. Same with this, same with this. Okay, so where do these come from? Well, let's use some implicit differentiation. Okay, so if y is this function here and I want to find dy dx, well, I can take the hyperbolic sine of both sides and then differentiate this. So let's have a look. So let's differentiate both sides of this one with respect to x. Okay, now we're going to do the product rule, the chain rule here. So okay, so if that's your dy dx, right? We know the derivative of hyperbolic sine is hyperbolic cosh. And this is just 1, right? If I differentiate x with respect to x. So you get something like this, okay? So the derivative of this is 1 on cosh y, okay? Now, you can show that that is just that by using basically the same thing that we used up here, this thing here. So find the square of that and then take the square root. Okay. Oops. Okay. So use the cosh squared plus shine squared equals, cosh squared minus shine squared equals 1 for that one. Okay, so you can simplify this. You'll get, yep, you'll get 1 plus. Okay, and so you take the square root, 1 plus x, root 1 plus x squared. So that goes there. Okay, so that's a simple but quite involved derivation of how you get that derivative into that form. Okay. Okay. So you can do that with the other ones if you want to, but like again, you don't need to memorize these things because you'll have them in the exam. Okay. All right, let's have a look at how we can use these derivative kind of rules, if you like, to do some specific problems. Okay, so let's look at a question like this. So who can tell me what kind of strategy might we look at for this differentiation? Who can tell me in the chat? People are a bit quiet in the chat. What strategy? Yeah, Azalea, I think you're right. So it's a function of a function. And so, yeah, Aiden. So why don't we try to use the chain rule and make the substitution u equal x squared. Okay, so if u equals x squared, du dx will be 2x. Okay, all right, so this is a u there. So we're going to change this with and I'm going to make the substitution u equals x squared. Okay, so du dx is that. d du of shine inverse or inverse shine is that, or with x replaced by u. So it's going to be 2x times 1 over root u squared plus 1. And now we want to get back to the original variable x. So we replace u squared with u squared squared. Which will be x to the power 4. Okay. So the strategy was to use the chain rule because it's sort of two functions combined, inverse shine and x squared. And, to do that, you just put two derivatives together. Okay, So that's sort of a mid-level one, but still hopefully very accessible. Okay, so moving on. Okay, determine the derivative of this. So who can tell me what might a strategy be for differentiating this mess here? Who can suggest something? Any ideas? Abdul Rahman, good morning. Let's have a look. It's a product, so let's try the product rule, right? So I'll let that be U and that be V, right? So the strategy here, use the product rule. Doesn't matter which way you label them, but if U is log X, U dash is 1 on X. And if cosh, if this is cosh inverse, then the derivative is down here. So it will be 1 on root this thing. Okay. So now it's just a matter of applying the product rule. That times that plus that times that. Okay. Oops. Can't spell. Okay, so it's this times this plus this times this. Okay. No, Abdul Rahman, I think that's fine, buddy. Is there a problem? Let me know. Product rule is good because you've got a product of two functions. So I think the product rule is totally fine, right? Yeah, not too extreme with this one. I think with these ones, the integration are more challenging than the differentiation. Okay. All right. Let's look at some more important and interesting examples. Okay. Now these look simple, but actually they're not so simple, right? But what we can do is we can make them simpler, right? So the most important identity here is something like this. Okay. Now this form and this form are slightly different. But what we can do, we can rearrange this to be similar to this, okay? It's just a little bit of algebra that we need to make ourselves aware of. So let me see if I can do that. Okay, so I'm going to do a little bit of algebra on this to make that 4 into a 1. Okay, so let me show you how we do it. Okay, so I guess I can just squeeze it up here. X squared plus 4 with the square root sign. I can write it like this. So I want to basically divide everything in the square root sign by 4. Okay, so watch how I do that. So that's a 2. Okay, so make sure you multiplied by 2 and divided by 2. So this and this are actually the same format. Now, hopefully you can see, well, this and this, the bottom anyway, is the same. And I will be able to integrate this using inverse hyperbolic sine. Okay, so how do we do it? Well, we can use a substitution. So let's call this I. So I'm going to get something like this. Yep. Okay, it's a little bit squished. Okay, so it looks like I've made this far more complicated, but what I'm trying to do is get back to this thing. Okay, and the 1 and the 1. So what I can do now is make a substitution, and let's say u equal this x on 2 bit. So du is going to be a half dx. You can see we've got a half dx there. Okay, so if I substitute that in, what am I going to get? I'm going to get du over, oh my goodness, that is pretty much the same as that. Hang on, I'm just going back to my fat head for some effect. Oh my goodness, we did the substitution and it actually reduced down to something that we knew. Okay, so what we can do now is use this, integrate it, and then find our final answer. Back substitute. Okay. So when you have expressions like this, it's very similar to this. And if you want to, you can just make a substitution, rearrange them, and get them into something that you already know. Okay. So this is moving more now to more difficult things. Okay, more difficult sort of questions. Okay. So let me I'm going to pull up Maple in the background and see what this looks like in Maple. So just give me a minute. Let me see if I can just log into Maple. Did anybody get their assignment back yet? And if so, how did you go? Were you pleased with your mark? Were you surprised? How did your oh, Nicholas, something for you to go and have a look at. So I'm just bringing up Maple in the background now, so just wait. So while I'm doing that, have a look at this one and see what you might do for this one. All right, so let me go over to Maple, and I wonder if anybody got 10 out of 10 for the writing assignment. Did anyone get 10? Let me know if you got 10 out of 10. Yeah, the assignment's out of 10. So let's say I wanted to integrate 1 over the square root of x to the squared plus 4. Okay, I just want to integrate that with respect to x. It's a bit bigger so everyone can see it. Okay. Oh, no, come back. I did the wrong thing there. Okay, there you go. Now, notice in Maple that that they use arc shine. Okay, so when they talk about arc something, they're talking about the inverse one. Okay. Oh, no, did you? That's a good question. Let me go back. You can obviously see Maple supports what I've got, but let me just show you what's happening in the question. It's a good question. So you're asking what happened to the 2. Is that correct, Dijant? Yeah. So look, du equals 1/2 dx. So there's your half. There's your half times dx. So that combined just goes to du, right? Because you're just drawing on that over there. Have you got it, Dijant? Yeah, that's okay. Sometimes these things are a bit hidden. So with this one, how might we sort of rearrange this to get something like that? Well, yeah, you can do it. So the way I would do it, and you can just do this using a little bit of algebra, is you take the 4 and you divide it in there, just like we did over here. And so the way I did it, you had something like this. So you divide the 4 in there, and you can write it like 3 on 2 times x all squared plus 1. Okay, so a little bit of algebra there. See if you can check that. But this is the way that you would that I would do it, and then you can let u equals 3 on 2x. So du equals 3 on 2 dx. Okay, so you make those substitutions. Oh, so okay, just rearrange that. Sorry, 2/3. Okay, so if you make those substitutions, let's call this integral j. All right, you can say, right, j is going to be, we'll make that, this is going to become u squared, right? Get something like this. Okay, so that's a 2/3, a half, and that. So you can obviously cancel those out, and you're going to get this. So now we know, right, I can integrate that. And I can get back to my x's through this one. Okay. Now, if you really wanted to, you can form a formula for these sorts of things. You don't have to sort of keep going back to this form every time. But it's interesting to know how to do, right? Okay. Well, let's look at the last question, and for that, I'm going to look at Maple. And so let me share my window with you. Okay, so let's look at the very, very last question of this course. Oh my goodness, the calculus is almost over. The pain is almost over. Oops. Syntax, it's always syntax, right? Okay, so I put that into Maple. Yeah, Carl, I will in a minute. Okay, don't worry. And you can see again, we've got the inverse hyperbolic tan function coming up. Okay, so we kind of know where we're headed. Let's go back to the other one for Carl. Okay, and so this is our very final question. Oh my goodness, it's the last one. So sad. They're tears. Okay, so let me know if you need me to move that, Carl. Okay, so this is our very, very last question. Oh, so sad. So sad. So let's call this I for integral. So this is a definite integral. And we know from over here, the derivative of inverse hyperbolic tan is this, and that's pretty much the same, right? So if I integrate this, I'll get inverse hyperbolic tan. Right, Carl, let me know if you need more time, mate. So this is it. And by the fundamental theorem of calculus, right? So this is 0 because we know the graph is an odd function and it goes through the origin. So our simplification is just this. Okay. 5. Whoa, 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 whoa. He's crying in Chinese, right? Whoa, 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 whoa. Ah, 5. Oh, whoa, 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 whoa. Well, in Kai language, though, 5 means laughing. So when you see that, I'm talking about the Chinese slang, right? Not the Thai slang. Ah, Steve, I lived in Hong Kong for a while, so I took some Chinese classes. I worked at the University of Hong Kong for a year. It was very good, and I've lived in mainland China as well, just on the east coast though. So, mm, yeah. Oh, really, Abdul Rahman? Like snorting as in laughing? That's great. Yeah, I'd love to come again. I would love to come again. Oh, yeah, I really, really like Asia, and yeah, it's a great place. I would love to go back to China. Okay, folks. Well, that is it. That is it. So, look, I'm putting my party hat on. I hope you've had a good time in this in the calculus. So feel free to ask me anything. We got 5 more minutes, and I'm going to turn everybody's audio on. And if they want to talk, you can. Yeah, it's hard to say goodbye, I know. But I've had a really good time teaching this course, even though I haven't met you, but I do hope that I can meet you maybe next year if you want to come to campus. Maybe you take another maths course or something and you might see me again. So yeah, thank you for everything. And good luck with your studies. And I hope you achieve the mark that you want to achieve in Math 1131. Yeah, let me know what's going on if you have any questions. Remember, the exam will be quite difficult, okay? So if you've maximized your mark for the pre-exam, then you're in a good position, okay? And yeah, you just got to do your best. You just got to do your best. So I think Captain Bill will be doing some revision after this, and then on Monday also. And there are some video recordings of past solutions. Okay, yeah, pre-exam is a surprise. I'm hoping everybody did really well. But if you didn't do well, that's okay. You just got to hope for the best in the final exam. Okay. So yeah, let me know. Let me know if you have questions. We still have like Eloisa, what do you mean? I haven't do the pre-exam. Is it that horrible? Do you mean the final exam? Yeah, it is. It is more difficult. Yep. But the way the School of Mathematics uses it is to decide, well, this person gets a high distinction, this person gets a distinction, this person gets a credit. So pretty much everybody can pass this course, right? Almost everybody. But it's then, well, do you want to pass or do you want a distinction or a high distinction? So the students that do really well in the final exam, they tend to get a high distinction. I'll show you the recordings. Let me have a look. Yep. So, it's hidden at the moment. Let me just see. Oh, yeah. Yeah. So I'll just share my screen. And so this is in the, I don't know if this is available or hidden, I think, but here it is, there are solutions, live streams, all sorts of things. Okay. So I guess I can put you can try it, see if you can find it. Okay, if you can't find it, then it might be released later, like maybe in a couple of days or something. Yeah, the exams do change, Steve. So, yeah, you just got to try to prepare the best and look at the past exams, and pretty much everybody should be able to pass the course. Okay, any more questions before Captain Bill arrives? Oh, there you are. Hello, Captain Bill. I'm celebrating because it is the final calculus lecture.
Excellent.
Yeah. So, yeah, hello, Captain.
Yeah.
So we're just talking about the exam. So Ashwin asks in the chat, what's the average mark in the final exam? Pretty low. Yep. But don't be scared, Ashwin. Like just give it your best shot. Thank you, Eleanor. All the best. Well, everyone, we will see you later. And yeah, Captain Bill will be doing some revision and next week. And yeah, thank you for everything, Abdul Rahman. And we'll say goodbye. And let's see if hope to see you all on campus next year. And smash that final exam. Smash it. I hope you get 100%. I hope you get everything that you want and that you deserve. Okay. So yep, I'll sign off, and it's been great. And yeah, thanks everyone once again. And I will hand you over to Captain Bill.
See you later,
All right.
Chris.